All right, I'm going to be working through the Spring 2024 Exam 2 for Calculus 1, Math 2144 at Oklahoma State University. So the first question is a multiple choice question. And it says that we have f of 6 is 11 and f prime of 6 we know is 1/4, and then we know that this information about the second derivative is positive. So if we're going to take that information, one thing we might do is kind of graph it, so we know that when x equals 6, the function is at 11, not 10, 11. So I know that is a point on my graph. And then this is telling me the slope of the tangent line at that point. So I know that that slope is 1/4, so it's going to be kind of like that. So if I were to write the equation of that tangent line, I'm going to use the linearization formula. So the linearization is equal to f of a plus f prime of a times x minus a. And here my a is 6. So my linearization of x is going to be f of 6 plus f prime of 6, x minus 6. And I know what f of 6 is. It's 11. F prime of 6 is 1/4, x minus 6. Okay. And then I'm asked to find the best linear approximation for f of 6.5. So I can say f of 6.5 is approximately equal to the linearization at 6.5. And so I can plug that into the linearization formula here, and I get 11 plus 1/4 times 6.5 minus 6. And so the answer that we get from that is 11.125 when I do that. So it's either going to be E or F. And so the question is it an overestimate or an underestimate? Well, I'm going to use this information that I know about the second derivative. The second derivative tells me that the actual function is concave up here. So it goes through that point I know, but it's concave up. So because that function is concave up, I can see that the function is going to be above the linearization as I go to the right. So when I go from 6 to 6.5, the linearization at 6.5 is going to be below the linearization, or below the actual function value. So I can say that linearization is an underestimate of f of 6.5 because the linearization is going to be below the function value because of the concavity. Okay, the next one says I have a 3,000 volume box container with a square base. The material to construct the top and bottom costs 3 cents per inch, while the side faces cost 2 cents per square inch. So we're going to need to draw a picture of our box. And we're told that the base is square. And so we might say that this base is x, and then this might be, we could call y. And so the cost is going to be, there's going to be a cost for the top and bottom, and then a cost for the 4 sides. Okay, and so that will be the cost of the top and bottom is going to be 3 cents per square inch. And I know the top is x squared and bottom is x squared. So 3 times 2x squared. Plus, for the sides, I know that they cost 2 cents per square inch. And I have 4 of those. So 4 times 2 cents times x times y. So, so we can start to see that some of these look like the cost functions that we have here. But one thing we might notice is that all of the cost functions over here are in terms of x alone. And so one of the things we might need to do is change this y here into something that has to do with x. And so the thing we haven't used yet is the fact that the volume we know is 3,000. So that tells me that x times y is equal to 3,000. Or in other words, y is equal to 3,000 divided by x squared. So I can plug that in for my y. So that gives me 6x squared plus 8x times 3,000 over x squared. And now I can start to see which one that's going to connect with. And so the 8 times 3,000 is 2,400. And then the x divided by x squared is going to just make a plain x on the bottom. And so the answer for that is going to be, hang on. By solving for which of the following equations can we determine the value of x for which the cost of the box is minimized? Okay, so, all right, so this is my cost function. So let's see if we can answer the question. By solving which of the following equations can we determine the value of x? So what I want to do is the value of x, it will be c prime of x equals 0. So, so what is c prime of x? Well, I would need to take the derivative of this function. So again, my function is c of x is equal to 6x squared plus 24,000 over x. And I could write that as x to the minus 1. So then c prime of x will be what? It'll be 12x minus 2,400. 24,000 x to the minus 2. So that's what I want to set equal to 0. So that would be this answer here, D. So I'm saying 0 is equal to that derivative function. Okay, on this one, I'm given the graph of the derivative of G. So that's the derivative. And I want to identify which of the following statements are true. Okay. So the question is, are x2 and x4 critical points of G? So critical points of G would be values when G prime equals 0. So at x2 and x4, is G prime equal to 0? Well, I'm given a graph of G prime, and I can see that the value of G prime is non-zero. It's positive, something positive. So that is incorrect. Next one, G of x3 is a local extreme value of G. Okay, so I can look at x3, and I can see if I make like a G prime line, I can see that when G prime equals 0, that's going to be at x1 and at x3 and at x5. And in between those, to the left of x1, my G prime is negative. To the right of x1, between x1 and x3, G prime is positive. Between x3 and x5, G prime is positive above the axis. And to the right of x5, G prime is negative, which means that G is decreasing here, G is increasing here, G is increasing here, and G is decreasing there. Okay, so is it true that x3 is a local extreme value? Well, I can see that x3 is neither a max nor a min because G is increasing on both sides, so 2 is false. Next one, x1, x3, and x5 are critical points of G. That is true because they are values for which G prime is 0. Next one, x2, G of x2, and x3, G of x3, and x4, G of x4 are inflection points of G. Okay, so to tell if they're inflection points or not, I need to see if the concavity changes. So if I'm looking at G prime and I'm trying to tell things about G double prime, I want to see where G double prime is equal to 0. So G double prime will be equal to 0 when the derivative of G prime is 0. So that will be at these values. So x2, x3, and x4 are the places where the derivative of the derivative is 0. In between those, I can see that G double prime, if G prime is increasing, that means G double prime is positive. If G prime is decreasing, that means G double prime is negative. If G prime is increasing, that means G double prime is positive. And if G prime is decreasing, that means G double prime is negative. Okay, so what does that mean? That means that if G double prime is positive, that means G is concave up. This means G is concave down, G is concave up, G is concave down. Okay, so I'm wondering if they're inflection points. So at x2, x3, and x4, we see a change in concavity at each of those points. So 4 is correct. Next one, G of x1 is a local minimum of G. And so if I go back up here and I look, I can see that at x1, G goes from decreasing to increasing, so that is a local minimum. So 3, 4, and 5 are all true. The correct answer is E. One thing to remember here is that if what we know about F, if F is concave up, that means that F prime is increasing, and that means that F double prime is positive. If F is concave down, that means F prime is decreasing and F double prime is negative. If F is increasing, that means F prime is positive. And if F is decreasing, that means F prime is negative. And so we can kind of see if we look down through here, I'm looking at when F prime is increasing and decreasing, tells me when F double prime is positive, negative, and it tells me when F is concave up or down. So those can kind of be a helpful way to think about what's happening and organize your information. Okay, for the next one, I'm given a portion on the graph of a function that passes through C, f of C. The question is, which of the following conditions are satisfied? Okay, so f prime of C, the first condition is f prime of C greater than or less than 0. I would say here that f prime is less than 0 because the slope is negative. So I can go ahead and rule out A and B. Then, is it true or not that what's going on with the concavity? So f double prime of x is greater than 0 for x less than c. So when x is less than c, is it concave up? That is true. D is false. And f double prime is less than 0 for all x greater than c. So f double prime being less than 0 means that f is concave down. And so f double prime is positive, and here f double prime is negative. So the correct answer is C. For the next one, I'm given a graph of f of t, and the question is that g of t is t squared over f of t. The question is, what is g prime of 1? So I'm going to say if g of t is t squared over f of t, I can take the derivative of that using the chain rule. Low d high minus high d low over low squared. So g prime of 1 will be f of 1 times 2 times 1 minus 1 squared f prime of 1 over f of 1 squared. So what is the value of f of 1? The value of f of 1 is -3. And what's the value of f prime of 1? That would be the slope at 1. So I have f prime of 1 is 0. So when I plug those values in here, I get -3 times 2 minus 1 times 0 over -3 squared. So that gives me -6 over 9, which reduces to -2/3. This says to find the critical points of f. So the critical points are places where the derivative is equal to 0 or is undefined. So we'll start by computing the derivative. So f prime of x is equal to 6x squared plus 6x minus 12. And I want to set that equal to 0. I can notice that I have a common factor of 6, so I could factor that out. And then I can see if this factors. So let's see. So I want a -2 and a +1, so I want my 2 to be positive and my 1 to be negative, and then that's gonna work out. Okay, so then that gives me x equal -2 and x equal 1 as my two critical points. So then it says determine the absolute minimum and absolute maximum of f on the interval from 0 to 2. So one thing we might notice is that this critical point, 1, is on the interval 0, 2, but x equal 2 is not on that interval. So I don't have to consider that critical point. And so what I know here is that the absolute max and min can occur at endpoints or critical points. So the endpoints are going to be at 0. So I want to look at f of 0. I want to look at f of 1, which is my critical point that lies in the interval, and then f of 2. So those three values, one of those is going to be the absolute max, and one of those will be the absolute min. Now I just need to take those values and plug them into this function here. The quickest way to do that is to go to your graphing calculator and type that into your y1 equals. So you're going to type that function in, and then you can use the trace feature on your calculator to plug in specific x values. So I'm going to go to my y equals button, and I'm going to type in 2x to the third plus 3x squared minus 12x, and then plus 4, and I'll hit graph. But then I can hit my trace feature here, and I can just type in the value 0 and trace, and that will be at the y value is 4. And then if I type in the x value 1, I get the y value -3, and then if I type in the x value 2, I get y equals 8. So this one here is my absolute max, and this here is my absolute min. Okay. So for this one, I'm evaluating limits. So the first thing we want to do is determine if these limits need to use L'Hopital's rule, because that's kind of the new thing we've learned about limits in this part of the class. And so if I look at this first one and I think about as x goes to 0, I know that sine of 0 is 0, and I know that e to the 0 is 1. So the top of this is going to 0, and the bottom of this is going to 1 minus 1, which is 0. So this is an indeterminate form of type 0 over 0. So because of that, I can apply L'Hopital. Which means that I can take the limit as x goes to 0, and I can take the first derivative of the top and the first derivative of the bottom. So sine of x, the derivative of that is cosine x, and the derivative of e to the x minus 1 is just e to the x. At this point, I can, again, figure out what happens as x goes to 0. If I just plug in 0, cosine of 0 is 1, e to the 0 is 1, so I don't have an issue here with a 0 in the denominator. So this is just going to 1 over 1, which is 1. For the next one, I want to look at the limit as x goes to infinity. And so I can see that in the numerator, as x goes to infinity, that is going to negative infinity, because my highest power of x is this x cubed, and the leading coefficient of that is negative. So as x goes to infinity, that numerator is going to negative infinity. And the denominator is also going to infinity, because that e to the x is going to grow to infinity. That sine of x is bounded by 1. It doesn't get any bigger than 1 or -1. And so that denominator is also going off to infinity. So this is an indeterminate form of type infinity over infinity. Well, it's really negative infinity over infinity, but yeah. So L'Hopital applies here. And so I can take the limit as x goes to infinity of, I'll have 2x minus 27x squared over e to the x cosine x, e to the x plus cosine x. And so then as x goes to infinity, I have the same issue. I still have an infinity over infinity indeterminate form. So I can apply L'Hopital's again. And I get the limit as x goes to infinity of 2 minus 27 times 2, x, over, and the derivative of the bottom will be e to the x minus sine x. And then, again, I have the same issue that as x goes to infinity, the numerator and denominator are both going to infinity. So I'm going to apply L'Hopital's again, and I get the limit as x goes to infinity of negative 27 times 2 over e to the x plus, minus cosine of x. And what I can see is that that denominator is going to go off to infinity, and the numerator is a constant, so this is going to 0. Okay, for the next one, I'm looking for the limit as x goes to pi over 2 from the right-hand side. And so secant of pi over 2, let's see, secant is the flip of cosine. So if I think about what's happening at pi over 2, secant of pi over 2, since cosine goes through 0 at pi over 2, secant of pi over 2 goes off to positive infinity. And then I have 1 plus tangent of x, and so tangent of pi over 2 also is going off to infinity. So this is an indeterminate form of type infinity over infinity, so I can apply L'Hopital's. So this is equal to the limit as x goes to pi over 2 from the left of the derivative of secant is secant x tangent x. And the derivative of tangent is secant squared x. So this reduces to the limit as x goes to pi over 2 of tangent x over secant x. And so then I still have the same issue, so I can apply L'Hopital's again. This is the limit as x goes to pi over 2 of secant squared x over secant x tangent x. And we seem to be stuck in a loop here, so maybe this is not the right approach. Okay, let's hang on a second. Can we rearrange this in terms of sine and cosine? After the first L'Hopital, we'll get the limit as x goes to pi over 2 from the left of secant squared x over secant x tangent x over secant squared x. So one of those secants reduces, so I get the limit as x goes to pi over 2 from the left of tangent x divided by secant x. So what is that? Tangent is sine over cosine. And I'm dividing by secant, which is dividing by 1 over cosine. So that's be multiplying by cosine x. So then that cosine over cosine will cancel. And then this gives me, I could just apply that. So sine of x at pi over 2 is going to 1, so this is equal to 1. Okay, so that's what we needed to do. All right, for this one, I want to find h prime of 2. So let's find h prime of x. H prime of x is going to be, I'm going to use chain rule multiple times. So the most outside layer is the f, so I'm going to be f prime of, I'm going to leave the inside alone, g of x squared times, now I'm going to deal with the squared, 2 times g of x to the first. Maybe I won't write the first power there because it looks like a prime. And then times the derivative of the inmost part is g prime of x. Okay, and so then I just need to use the table to evaluate that. So I'll use the table here to evaluate all of these things. So that'll be f prime of g of x squared. So g of 2 squared times 2 g of 2 g prime of 2. So that's going to be f prime of, so g of 2 is 1, so 1 squared is 1, times 2, g of 2, again, is 1, and g prime of 2 is negative 4. And f prime of 1 is 3. So this is 3 times 2 times negative 4, which gives us negative 24. Okay, so then it says if s of x is equal to x squared arctangent of f of x, then s prime of 4, so I'll need to compute s prime of x. And so s prime of x will be 2x. I'm going to use product rule. I have product rule here because I have two functions multiplied together. Arctan of f of x plus x squared, and the derivative of arctan is 1 over 1 plus x squared, but my inside part is f of x. And then I'm going to multiply by that by f prime of x. Okay, and then I want to plug in 4 to that. So that'll be 2 times 4 times arctan. F of 4 is 0. Plus, I'm plugging in 4. So 4 squared times 1 over 1 plus f of 4, f of 4 is 0. And then f prime of 4 is also 0. So this thing, arctan of 0 is 0. So I just end up getting 0 for that whole thing. And then I'm looking for k prime. So k prime is going to equal, so it's 2 to the g of x times the natural log of 2 times the derivative of the inside function, which is g prime of x. So I applied chain rule to that. And so if I evaluate k prime of 1, that's going to be 2 to the g of 1, natural log 2, g prime of 1. So that's going to be 2 to the g of 1 is negative 1, natural log 2, and then g prime of 1 is 6. So there's my answer to that. Okay, problem number 9. Again, I'm trying to find f prime of x. One thing to notice here is that I have my pi as a constant, and then this e to the pi is also a constant. So it's just like a constant x to the constant. So f prime of x is going to be pi times, I'm going to take the constant, the power of x, bring that down. So that's going to be e to the pi. X to the power is going to be reduced by 1. So e to the pi minus 1. So that's f prime. Next I have y equals sine of x. Find the second derivative with respect to theta. Okay, so if theta is in degrees, that's equal to 180 over pi times theta in radians. Okay, so so maybe I'll use a different variable here. So if y equals sine theta, so y equals sine of, I'm going to call it 180 over pi times beta, I don't know, there. And so, so I want to find the second derivative. So y prime is going to be cosine of 180 over pi beta times 180 over pi. And then y double prime will be negative sine of 180 over pi beta times 180 over pi times 180 over pi. And so y double prime is going to be equal to negative sine of, remember that inside part is what we're going to call theta, times 180 squared over pi squared. So that's what that is going to be. And so I'm using this to convert from theta in degrees to theta in radians, where I'm using that beta to be my theta in radians. Okay, so find dy dx for that curve and solve for dy dx in terms of y and x. Okay, so I need to take the derivative implicitly with respect to x. So the derivative of y with respect to x is just dy dx, minus the derivative of secant is secant tangent, so it'll be secant tangent, and I'll leave the inside function alone, which is 4 to the y, times the derivative of 4 to the y, which will be 4 to the y, natural log 4, equals the derivative of x times y, that's a product rule, so I'll have 1 times y plus x times dy dx, and then plus the derivative of sine is cosine x. And I want to solve that for dy dx. So the first thing, oh, dang, I missed a dy dx. 4 to the y, natural log 4 dy dx. Okay, so let's look for all the places where we see dy dx. I see one here, I see one here, and I see one here. So that's this term, and this term. So I want to take the terms that have dy dx and put them on one side, and the terms that don't and put them on the other side. So I'll have dy dx minus secant of 4 to the y, tangent of 4 to the y, 4 to the y, natural log 4 dy dx, minus x dy dx equals y plus cosine x. Then I can factor the dy dx out. 1 minus secant minus x, sorry, I forgot that, equals y plus cosine x. And then I can divide by that stuff. So I'll get dy dx is equal to y plus cosine x divided by all that stuff in parentheses that I have there. Okay. Next one, I have Nathaniel wants to construct a garden in the shape of a sector that will be bordered by brick pavers. Okay. The area of the garden will be 60 square feet. Okay. R represents the radius of the sector, and theta represents the measure of the interior angle in radians. Determine the values of R and theta that minimize the amount of pavers Nathaniel needs to buy. Okay, so what I want to do is, okay, so I know the area of the garden is 60 square feet. So the area of a sector is going to be pi r squared times the portion of the circle times the proportion of the circle, which is going to be theta over 2 pi. So that gives me, my r is that capital R actually, and so I know that is equal to 60. Okay, so that tells me that capital R squared is equal to 120 over theta. Okay, and so then, or maybe I want to solve that for theta. What do I want to solve that for? I'm not sure. Let's solve for theta. So theta is equal to 120 over r squared. Okay, and so that's the area of my sector. So that's how I can relate theta and r. And then I want to say the distance around the garden. Okay, so if that's r and that's r, this is r theta. So then the distance around is going to be 2r plus r theta. So this is my okay, So this is my pavers. So this is my distance, I guess. And then I can plug in what my theta is. So my distance is equal to 2r plus r times 120 over r squared. So that's going to be 120 over r, or 120 r to the minus 1. And so then I can take the derivative. And so I get 2 minus 120 r to the minus 2. And then I can set that equal to 0. And I can solve for r. So I get 120 r to the minus 2 is equal to 2. I can divide that over. And then I can take both of those to the minus 1/2 power. So I get square root of 60 is my critical point. And then I need to check that that is a minimum. So I can look at d prime, and I can look for values below and above square root of 60. And so if d prime is, so if I plug in a value that's greater than 160, or square root of 60, so I'm just going to plug that into my calculator. So I did 2 minus 120 divided by x squared. And so what is square root of 60? Square root of 60 is about 7.74. So I'm going to plug in a value in my trace. I'll plug in like 6, and I get something negative. And if I plug in a value greater than 6, square root of 60, I'll plug in like 8, and I get something positive. So d prime of 6 is negative. D prime of 8 is positive. And so I've checked that this is actually, in fact, a minimum. So that means d is decreasing here and increasing here. So it's a minimum. Okay. Justify the dimensions, minimize the perimeter. Okay. Yep. So we're done.